Oh, it's the first stage. So, it's the first one.
Welcome to the Analytical Lab. My name is Joy Malaba. I'm the Analytical Research Scientist here. I will take you through the instruments that we have and I'll just give you an idea of what we do here. So my work here, I support researchers to do different research testing analysis. I also help with data, proper data, like once we get the analysis done, being able to analyze the data and being able to publish that. So this analytical space is a very important resource that we have in the university because we're able to do multiple testings here, support researchers here, not only in the Russ College of Engineering, but within Ohio University. And in the long run, we plan to open it up to people outside industry, collaborators, and people outside Ohio University to be able to do testing for that. So apart from testing, we also offer training to graduate and undergraduate students to be able to have hands-on training on the instruments, what they've learned in class, and being able to correlate that and being able to actively use the instruments. So here I've divided the instruments into 6 main sections and I'll take you through them. So we have the elemental analysis instruments that we have. Here we have a carbon, hydrogen, nitrogen, sulfur and oxygen analysis. So it looks for all these elements within the samples that we test. So let's say we bring in the soil samples here, it burns up the sample and then it produces measurable gases. So then we're able to know, let's say if it produces nitrate gases, we're able to know there's presence of nitrogen within this particular sample. So we also have a total organic carbon analyzer. This one here. So the total organic carbon analyzer measures organic carbon present within a sample. So the more organic carbon we have within a sample, the more contaminated the sample is. So let's say if you have drinking water and it has a lot of carbon, organic carbon in it, there's contamination in it. Also, let's say if you have wastewater and there's a lot of carbon in it, we know that this is going to pollute the environment. So we will have that treated before it goes out to the environment. We also have the second set of instruments. We have a surface analysis instrument. So we have a chemisorption analyzer, which looks at the different active pores within a sample. So let's say you have a sponge and you're trying to if you put glue on it, you want to see which areas this glue can be able to attach itself to. So we put a gas over these different surfaces and we're able to measure that and see the absorption capacity of this particular sample. Then on this other side, we have a porosity analyzer, and we can move forward to have a look at this side. So here, this porosity analyzer measures the surface area and pore volume of the samples that we have. So looking at the surface area, we can have a powdered sample that has a powdered particle that has a surface area equivalent to a football field. So we're able to get more information about the different surface area of the different samples we have and the pore sizes of those particular samples. Then the next set of instruments we have, I call them the sample preparation instruments. So these sample preparation instruments just help us in the preparation of our samples into a more suitable matrix that is suitable to the instruments that we're going to analyze. So we have a digital reactor, a microwave digester. These two, I like them because they speed up the process of breaking down. Let's say if you have a soil sample, you can introduce an acid for the microwave digester and it breaks it down in 15 minutes for a process that would have taken 2 hours or more. Then we have our energy analysis instrument that's behind here. It's called a calorimeter. When you hear the word calorimeter, you can see calories, right? So it's able to measure the amount of calories within a particular sample that we have. So what happens is it burns up the sample, then the heat that is generated from that, it's spread out to the water sample that's around the vessel that the burning has taken place, and we can be able to measure the amount of calories within the particular sample that we have.
So you could use that for food?
Yes, we can use it for food also.
Yeah.
Yeah. So here we have chromatography systems, and we can move forward to have more vision of that. So we have two chromatography systems. We have an ion chromatography system. Chromatography is separation of mixtures. So here we're able to separate ions. Let's say we have a salt sample. When salt is dissolved in water, we have the sodium ions and chloride ions. So the sodium ions are positively charged ions, which can be detected by the cation analyzer. And then we have the chloride ions will be negatively charged, and they can be analyzed by the chloride and anion system there. So we can be able to actually run two sets of analysis concurrently at the same time. Then we have the gas chromatography instrument there, which also now separates samples that have been volatilized into gaseous forms. So we can be able to even separate, be able to separate between a mixture of perfumes or fuels, or let's say in the case of arson, when arson has happened, we can be able to break down this sample and test and see what fuels were used within for that particular incident. Then the last set of sample instruments I have are in this room. I call them the spectroscopy and imaging instruments. So we're looking at the interaction of light with different samples. So you could have the UVV produces ultraviolet and visible light, which shines on your sample, and we're able to measure the amount absorbed. What is absorbed there? We're able to get the UVV's data from that. We have the FTIR instrument in there, which has infrared light that's now used to measure the functional groups within the particular instrument that we have. So it kind of goes deeper from the UV. The FTIR goes deeper and gets the functional groups and the kinds of bonds that are within a particular sample that we have. Then we have the Keyence microscope, which is a digital microscope that gives us more visual of the surface, and it can magnify our samples to about 1,000, which is quite good. And so we have capacity of growth for this analytical instrument, and we plan to have a lot more other instruments also coming in. So I hope you've enjoyed this, and you'll get more as you move to the other labs. And feel free to ask me if you have any other questions. If you have any questions, yeah. Yes.
Thank you.
Since this is set up as a shared, this seems like it's set up as a shared facility.
Yes.
So are you expecting people to prepare their samples before they come
They
here?
could, yes.
And
They
then-
could prepare their samples if they know how to. If not, we can be able to work together towards preparing the samples.
So
and
you're planning to
getting
use
them
this
out.
space to do sample preparation also?
Yes.
Okay.
Yeah, because we have a few wood there and some spaces here. Yeah. So we hope that we can get more research going on within the facility. Yeah.
Okay.
Thank you.
Any more questions before we keep moving? All right. We can head on to the next station. I'd like to go on.
Thank you. Thank you.
Thank you.
We're actually going to heading in this direction. Hi. Hello, welcome. We can start 5 minutes.
Hello. Welcome. All right. Welcome, everyone. My name is Savaskaya. I'm one of the professors at Electrical Engineering Computer Science. I work with the electronic materials, electronic devices, and their applications to novel circuits, even systems. So I work kind of at many layers of engineering at the electrical engineering side, but in order for us to apply them to electrical engineering, novel materials needs to be studied. Most of these novel materials are nanomaterials with unique properties that require microscopy. So it's all begins and often even ends back in microscopy to see these whole systems made from novel materials. Behind you is a three type of tools that we have in this small lab. It's called Nano Studio. This one is for undergraduate nanotechnology introduction. So what we do here is we bring undergraduates to come and learn about these tools, which are not typically available at the undergraduate curriculum. So graduate students use these tools, and often when they are ready, but we using these select tools, we are able to get undergraduates engaged in novel research. On the left is a spectroscopy tool. This is basically studying the light transmission and reflection from novel media. This could be wet solutions or layers, thin films, and the spectroscopy tool allows that for that optical measurements. Behind this is the atomic force microscope. What you are seeing, atomic force microscope allows basically the following. You have this cantilever, which is this diving board, this little diving board. It is basically has a very sharp tip underneath, and it oscillates like a musical tuning fork, and it interacts with the surface while in resonance. And then we can look at how these different points on the surface changes properties of the resonance and net out an image. And this image is so accurate, you could see behind some of these images in this type of materials. You can actually get atomic terraces. If you're doing very high quality surfaces, you can even get atomic resolution in this device. But if you are seeking atomic resolution real devices, this one, it is called scanning tunneling microscope. So this is a different variance of this, whereas we can go on any surfaces on atomic force microscopy, we can press against surface, look into softness and different properties. In this tool, conductive surface to conductive metal tip, you get exceedingly close but not touching, and electrons start jumping quantum mechanically, and you can map out atomic height differences, which will show up in this very sensitive current measurement. So you can actually map out the positions of atoms if the surface is very clean, and it's typically under vacuum at low temperature. But with this device, you do in the undergraduate education, this is good. We can do in select materials like graphene, you can actually see, or graphite, you can see the carbon atom positions with this device. Over here, in the other lab, in this other lab, we have two electron microscopes. So in this facility, we have two electron microscopes. You are seeing a live image on one of them and a stored image. So both of them are electron microscopes. We have a third room for a novel electron microscope that will hopefully come up soon. This will be state of the art in terms of resolution and capabilities. These are very good devices as well. You can see that this is a live image of, you can see in the electron microscopy, you go from millimeter scale to micron scale. You can see it's 20 micron, that bar, to nanometer scale, all in one device. This doesn't give you all the capabilities, let's say, of testing, touching the surface and mechanical properties, but you could learn a lot. For instance, in this version, this has X-ray detector in it, so that electron beam hits the surface, X-ray comes out in tiny amounts. So we can map out elemental distribution. What you are seeing in this colorful map is a distribution of oxygen, I believe, the iron, magnesium, and chlorine. Okay? So we had a map of elements on this image, which otherwise wouldn't look like this. So you can see this image is the normal black and white image like that, which is the morphology. And if you switch to the X-ray mapping, you see the elemental mapping of which element is where. For instance, this is a sample, I believe, from corrosion lab. So they have seen where the corrosion, how it proceeds. So when you learn at atomic processes, then you can really apply to novel applications. The noise is the chiller that we hear from chilling that used to happen in one of the pumps that normally work at elevated temperatures. So this is for X-ray mapping. This is for morphology, and one more property we have. We are undergoing changes on the system. We will take the electron beam and write shapes as small as 20-30 nanometer. So this will also be converted. It's being converted. We had a similar system like that in the older facility to electron beam writer. So not just an investigation tool, literally an electronic pencil, where you write the electrons on surfaces at extreme resolution.
So you said this came from the Persian lab right here in OU?
I believe so. I believe so.
What they were looking for with the signal?
Typically what they see is they see which element accumulates at what kind of situation.
Okay.
Because some elements are more conducive to corrosion than others.
Okay.
So they can look at how the corrosion starts, propagates, because what typically they do is they have passivating layers that cover the surface so the metal surface doesn't even corrode in the first place.
Okay. Thank you.
Does anyone have any more questions?
Yes, welcome. Any questions, welcome. The other room is very unique because this is a graduate research facility, by and large, research labs here. We engage undergraduate students in that lab and in this lab, microscopy that lab for more analytical techniques and wet lab, so that they can be trained and then become part of the bigger story in the research labs.
Yeah, one other question. And then your scope over on this side, you said the one that's got the arm and then point. How small is that point?
So depends, you can buy the ones as tiny as 1 nanometer, literally, because it has carbon nanotube and the or typically they come to a chrome about 10 nanometer radius.
Is the scanning electron microscope in there the one that was down in the electroengineering research center, or is this
Good question. That one, it was a transmission electron microscope. Unfortunately, we no longer have it. University decided not to keep it because it's a very high cost equipment in terms of maintenance and where it needs to be installed. It was very problematic. Where it was installed, it was an isolated slab. We have an isolated slab in this lab. The next SEM will have maybe TM capabilities as well, but they are going for a system called focus ion beam writer, which will have electron microscopy as well as focus beams of ions to literally etch, make holes, take cross sections live in 3D microscope. So we kind of sold the system out to buy something that's more capable for type of research happening in this lab.
the all on this? It was sold?
Yes, it was sold to Stanford University Grant Task Force. Thank you.
Do you have that yet?
No, not yet. This room is
It's
empty.
not even in there.
No, the room is empty.
I was just wondering, I thought maybe you were still
Right.
setting it up or something.
I personally didn't want that TM to go,
Yeah.
but it happened at a time where we needed to vacate that lab just during COVID, and we needed to find a location. We could not find a suitable location and keeper for that $1.5 million system that was basically going to sit for a while, and it was only going to maybe deteriorate, so we decided to sell it at the time. But we do have other TEMs in the lab. Again, that was atomic resolution. That was very high-end system. But the new system will be still atomic resolution, I believe, except it will be more TM. The new system with the capability of focus ion beam, you will create clean surfaces and look into it live, which is a unique property, of course. Thank you.
Let's keep going.
Yes.
Thank you very much.
It's a pleasure. Thank you. It's great to see you all. Appreciate it.
Yeah.
We're gonna head this way a little bit.
Leave without saying
We have some people who want to know a little bit more about this area.
Tell the other guy that's hard to remember that. That's why I call you attention.
All right, well, welcome. My name is Guy Riefle. I'm the chair of Civil and Environmental Engineering. And I was introduced to acid mine drainage soon after I got to Athens, Ohio. It's a common environmental problem in southeast Ohio. And it's from these old abandoned coal mines that release pollution into our streams. And this is one of them. This is one of the biggest in the region. It's True Town Sea. And this is what it turns our streams to look like. It turns them orange. So I looked at this and I said, so rather than treating this as a pollutant or an eyesore or something that we should be embarrassed about, what if we could sell it? What if we could use this as a product and commercialize it? So we set out to develop a process where we could collect the water, treat it, and collect that orange color and turn it into a paint pigment that we could sell. My collaborator is John Sobra, who is the chair of art and drawing at the university here, and we commissioned this work of art from him, which he did for the building. It's permanently here, and you can see in the top there's sort of a pattern there. That is the original mind map for True Town. It's about 30 square miles of underground cavern that's all interconnected. They call it a room and pillar mine, and you can kind of see it's filled with a bunch of rooms all connected with corridors. So we collect the water, and we've been working on all the steps of it, dewatering it to produce a sludge, and then drying it, and we're now able to produce several different pigments. This is like the raw pigment that we get. When we heat treat it, we can turn it red or purple. And we've been working with the company Gamblin, which is one of the leading artist paint companies in the United States, and they are now selling our oil paints made with our pigments. And it's been such a success, they've asked us for more and more pigment, and they want to make this violet part of their permanent collection, which is really exciting for us.
What's the mineral that gives it that color?
It's iron. It's iron. It's one of the original pigments that mankind ever used. It's in the cave paintings. So
how much water do you have to collect to just get a small amount of pigment? Yes.
I've done this work by 5-gallon bucket. That's that's my unit of measurement now. A 5-gallon bucket makes about a tablespoon.
Oh.
Wow. So how much to get that jar right there?
A lot. Well, this seep produces 1.5 million gallons per day of polluted water.
Ooh.
And there's 350 milligrams per liter of dissolved iron in there. You do the math, it's about 6,000 pounds of iron going into Sunday Creek every single day. It's like someone's going out there and junking 2 cars in the stream every day since 1970. And so 6,000 pounds a day. We can sell this for about $1 a pound, which doesn't seem like much. That adds up to about $2 million a year in sales.
Wow. And I guess, do I dare ask how long it's going to be polluting for length of time?
There was a thesis on this in the geology department, and he came up with 250 years.
Oh, all right.
They're in their own business.
Yeah.
They were just kind of standing here.
All right.
That's amazing.
Anything else?
If I have any more questions, let's start moving forward.
Thank you.
Thank you.
Did you see that over here?
Yeah. Yeah, all up in Nelsonville and everything. Which I'm always amazed by that spring water that's up there. How that can come out.
Is that the Bob with it?
Yeah, he was.
So he did.
Is that what it is?
Can. Hi everyone.
Hello.
This is I'm one of the researchers here
My name's
today.
Hugh.
Nice meeting you. Hi. I'm one of the researchers here associated with the Institute for Sustainable Energy and Environment. Quick facts about the Institute. We secured over 39 million of external funding since 2008. We graduated over 20 graduate students, over 100 undergraduate students. We have over 10 patent applications and 2 license agreements. Our research capabilities include thermo-catalytic, electrochemical processes, materials R&D, process simulations, techno-economic, and life cycle analysis. I'm going to go take you through for a tour through the lab. Feel free on the way to ask me any questions if you have any questions. So please follow me. This is where our students kind of then we'll got our first stop going to be Richard, who's going to give us a quick overview of his research. Wait for it to go up.
He's looking at a little photo.
Yeah.
Okay.
All right, Richard.
Sorry.
My name is Richard Atta. I'm a PhD student in chemical engineering. So my research is basically about phosphorus and nitrogen recovery from wastewater. We are doing this to solve the issue of watershed pollution, which is caused by the release of phosphorus and nitrogen into the watershed. And so our basic solution is to use the electrochemical process to recover the nitrogen and phosphorus nutrients from the wastewater. And we are doing that into a form of a reusable agricultural fertilizer called struvite. So the electrochemical process uses electricity with very minimal chemical inputs. And it is also a very compact process such that you can integrate it into a wastewater treatment plant or a concentrated animal feeding operations. Yeah. Thank you. If there's any question.
No questions? Thank you, Richard.
Thank you.
We're going to go to the
You
next
said you have one. How
stop.
much power does this use? Going from, this looks like you got a battery right
Yeah,
down there.
so this is the power consumption for
Okay.
when we are using magnesium anode, we are consuming 127 gigajoules per metric ton of phosphorus, which we recover when we are using a magnesium anode and when we are using magnesium salt. So we actually tested two different magnesium sources,
Oh, okay.
magnesium metal and magnesium salts. So the salts has a lower energy consumption, which is 118 gigajoules per metric ton. So the energy we're consuming producing the struvite fertilizer using the different magnesium sources, compare that to the energy used in producing conventional phosphorus fertilizer. So this is MAP, monoammonium phosphate, diammonium phosphate, and triple phosphate.
Okay.
So these are the energy consumptions of these three these fertilizers are already in the market, and this is what we are making. So comparably, using magnesium chloride to produce a struvite fertilizer, I mean the energy consumption can be compared to the DAP, and this is the carbon dioxide emission from the process as well, which is also
Okay. Awesome, thank you.
Thank you.
Thank you, Richard. Our next stop is Quinn, who's going to talk about his research on CO2 mineralization. Quinn?
Hello everybody, my name is Quinn. I'm a senior undergraduate here at OU. Like Yaya said, my work has been on a CO2 mineralization reactor. Our end goal here is to trap carbon dioxide and prevent it from entering the atmosphere, causing a number of environmental problems. To do that, we're utilizing produced water. It's a liquid waste that comes from oil and natural gas fracturing, and it has a lot of calcium in it. And when you bubble CO2 through this liquid with calcium, you can combine the carbon dioxide and the calcium to form calcium carbonate, which is just chalk, essentially. So not only does this trap the CO2 and prevent it from entering the atmosphere, it also removes the calcium from the brine, which makes it a little environmentally safer. And that calcium carbonate can then be sold as a valuable industrial product to offset costs of the whole process and make it more economically efficient. You'll actually get a chance to see this reactor that we were testing with a little later in the tour, but I was just doing some preliminary research on this and studying the effects that some of the reaction conditions had on the rate that we were making that calcium carbonate. Anyone have any questions about any of that?
Will this work in a mixture of gases?
Yes,
Like,
yeah.
CO2 mixed with other things?
Yeah, the gas that we're using is flue gas. It's like the byproduct of burning coal and natural gas. And it has a number of other gases in it, but we found that those aren't affecting the precipitants that we're getting. It's just removing the carbon from that. You'll obviously then still have to deal with any sort of NOx or anything else that's coming out of that, but this is a way to remove that one particular greenhouse gas.
Is the calcium carbonate stable?
Yes, yeah.
Break down again?
Yeah, we were finding, one of our other things that we were examining was some of the different speciations of that calcium carbonate. We were finding that almost everything that we're getting was calcite, which is the most stable form, so it'll last for a long time.
All right, any additional questions for Quinn? Thank you, Quinn.
Thank you guys. Enjoy the rest
So
of the
now we're
gonna
gonna
bowl.
go through the lab.
Yeah, we got a meeting at 3, so.
Okay.
Thank
It was
you.
awesome. Thank you.
Fantastic.
Got class.
Evening?
You got class, sorry.
Oh, okay. We can continue now, safety losses. All
Do
right.
I need to write them now?
Huh?
Do I need to write them safety lab?
Yes, please. We're gonna go through the lab.
Okay.
So our next stop. Abby, they're gonna talk about their research.
Hello, I'm Ashley Clayball. I'm a master's student here at the university studying chemical engineering.
Hi, I'm Abby Paul. I'm a PhD student studying chemical engineering as well. Our work is primarily focused on developing a domestic supply of graphite for use in batteries. So my work has been focused on utilizing coal and turning that into graphite. And we've been doing a lot of work with lithium-ion batteries, but we also have been investigating other chemistries such as lithium sulfur, sodium-ion, a variety of different batteries. And so that's important because the US does not have a domestic supply of graphite, and so we're trying to kind of bring in the production back to the US.
And my research is kind of along a similar vein where I'm also studying lithium-ion batteries that have polarized materials in them, but I'm also kind of expanding that and looking at batteries that have multiple types of active materials in it. So I'm also adding silicon into the mix and basically testing to see how these materials kind of interact with each other when the batteries are cycling, and also just trying to see if we can find combination of materials that can have higher performing batteries in the end.
And then we have some examples of batteries that we've made here. These are, well, these were made at the University of Michigan, but we now have equipment to make them here, which is very exciting. These are called pouch cells, so this would be, this is kind of like a smaller version of what you have in your cell phone. Larger scale, or these are what are in your electric vehicles. And then we make coin cells using the glove boxes that are in the back to make, kind of do our preliminary testing with different materials because they require lower amounts of material. Hands-on. Yeah, pretty much.
Just in case there's a lot of people in a group.
There were more people until a second ago.
You just downsized a little.
Yeah.
That's good.
So what do you find with the silica? Is that
So one of
clear to me what the role of that is?
Yeah. So the thing with silicon is it has a much higher capacity than graphite alone does. Capacity just means kind of like how much energy the battery can hold. So it's really good to have a high capacity, but the downside with the silicon is that it expands a lot more volumetrically, and so when you're cycling, if it's like expanding and contracting, that can cause damage to the battery. So it's a little bit of a challenge where you try and figure out like how can you combine the two in a way so that way the silicon contributes more capacity to the battery but doesn't cause damage to the battery. So that's kind of one of the things I'm looking into. Yeah.
Alright, any additional questions? Thank you both.
Thank you.
Thank you.
Alright, so our next stop.
Hi, my name is Philip Yamasa, master's student in chemical engineering. Here with
Florence, PhD student in chemical engineering.
So our research is focusing on treating produced water, which is the water that is associated with oil and gas extraction. When you extract oil and gas, you normally have a lot of water coming out with it. In the US alone, we produce about 25 billion barrels of that annually. And majority of that just goes back into wells and has the potential of polluting underground and surface waters. So currently what we're trying to do here is treat this water to a point that we can use it for irrigation purposes or even if possible, drink it. But the problem we are having is these waters contain a lot of salts. So treating it is quite difficult and costly. Current treatments are about $8 per gallon of water, which is not that economically feasible. So we're trying to develop a treatment process that will be economically feasible and also produce water that can be used for irrigation purposes.
So you're working together on that? Is that okay?
So currently what we do is to do some chemical precipitation with sodium hydroxide to reduce magnesium with calcium in the water. And we are also trying to set up this electrochemical cell for removal of other minerals and such as sodium in the water.
Questions?
Where do you get this water?
So we get it from wells in and around Ohio. So we want to get, a representative water sample so that we can validate it and see if we can.
From hydroelectric.
Yeah.
All right, thank you both.
Thank you.
Now, for this track, research.
My name is Ferisha. I'm a PhD student here. And my research focuses on producing graphene from coal-based material. These are graphite, coal material. And we use electrochemical exfoliation process. It's like using electricity to separate a thin layer of graphene from this multi-layer graphite. This is an important project because we develop a cost-effective, efficient, and eco-friendly method to producing graphene. And unlike other people that use high quality and pure graphite, we use coal-based material. And these are some graphene material we produce. After testing, we found similarity between this material and commercial one. Then we want to use this material as energy storage devices like supercapacitor.
Great.
Are there any questions?
Thank you so much. Appreciate it.
I knew you were going to have a question.
Now to our next, well, we do have a lot of testing, materials testing equipment, testing from, thermal stability of materials to over here, mechanical performance with retention, flexural impact. So we are well equipped to run thermal, flammability, and mechanical testing on different types of materials. Our materials research is focused on polymer and metal composite materials, which is these are the next two stations that we're going to talk about this project. So Caleb Gula, one of my students, gonna give us a brief introduction about his research. Caleb?
Hi, my name is Caleb Gula. I'm Dr. Al-Majali's PhD student. I primarily work with coal and other carbonaceous materials. The video here to my left shows the continuous method for producing carbon foam from coal, specifically bituminous coal, developed here at Ohio University. The existing commercialized batch method has several limitations to it that takes manufacturing time up to several weeks to produce and costs several $100s a cubic foot. This limits its applications to low volume but high value expensive applications. Now comparing this to the continuous method produced here at Ohio University, we can decrease this manufacturing time from several weeks to just several hours, and then we can also decrease that cost from several hundred a cubic foot to under $100 a cubic foot. And this enables us to expand its utilization into market applications such as construction, aerospace, EMI shielding, energy storage, and even water filtration. Please let me know if you have any questions.
Thank you, Caleb. Any questions for Caleb? All right. Next is Grace.
Hi, my name is Grace Brannick, and I'm a master's student studying under Dr. Al-Majali. And so my project revolves around creating cool plastic composites for additive manufacturing. So first, we combine the cool powder up to 78% cool with the thermoplastics, and we then can 3D print mechanical test samples using commercially available 3D printers. And the target applications for this project are additive housing and composite tooling. And some of the benefits for using the cool plastic composites compared to some of the other traditionally used composite materials is that it has higher thermal stability, enhanced mechanical performance, and it also has lower CO2 emissions, and it lowers production and material costs. And this project is also revolving around thermal
thermoset plastics with creating a thick paste for direct integrated 3D printing, which the targeted applications for this research is for harsh environments. Do you guys have any questions or comments? Anything?
What kinds of things are you 3D printing?
So for the lab scale, we'll typically just 3D print mechanical test samples or thermal test samples, so we can assess, the mechanical performance, thermal capabilities of the cool plastic composite material.
So just the material.
Yeah, but we do have large-scale 3D printers in Building A, which I'm sure you guys will go see later. Yeah, and so there we can 3D print some prototypes for a wind turbine blade tooling prototype and a wall design prototype, since those are the two targeted applications that we have. But
There's a picture of a wall.
So this is really just designing the composite.
Yeah, so lab scale is mostly assessing like the material, seeing how it's getting its properties, seeing the printability of it, and then we have large scale printers, that will try to like 3D print prototypes.
Right.
From it. But yeah.
Okay.
So
Of course.
there's some tokens, if you'd like to take them, you can.
Okay,
But those are 25% cold plastic composite injection molded here at my university.
And what's the source of the plastic? Did you say that?
The types of plastic that we're using. For this, I believe it's HDPE, but we've also worked with like PLA, PETG.
Recycled plastics. We've used recycled plastics in the past, where this current is not. Specifically what
You're making new plastic.
we're taking virgin plastic and we're mixing it with a filler content, reducing the amount of plastic needed to produce your product.
But the application would be with recycled plastic.
We can use recycled plastic. We have used it before, but I believe that this material was just out of virgin HDPE. But yeah, we have used recycled plastics before, and we could.
So that the idea isn't to recycle the plastic; is to reduce the amount of plastic that we're actually using by using more of that filler content, and we can do that without reducing our mechanical and other properties, and it can still meet our application standards.
All right. Any additional questions?
Well, I have a lot more questions now.
Sure.
But that's okay. I was just wondering, so do you know the life, like what's the degradability of this relative to, and like what, in terms of like persistence, like a normal plastic would be?
Yeah, that's a very good question. So this is started when we looked first at replacing wood plastic composite with our material. So we've done on the product side, like this one here, we had more filler, that means less plastic. So we're able to achieve 70% and meet the standards and meet the codes. And with also we used recycled, to your point, we start from virgin plastics, and in some products we have recycled plastics. And then we expanded to additive manufacturing, where we looked at a lot more different plastics. Like we looked at PLA, polylactic acid, PE. We looked at polycarbonate, with many other plastics. Now, the reason we are interested in PE and we wanted to make it 3D printable. So high density polyethylene is not 3D printable. You now can go and buy a filament from the store that's PLA. But there's not enough of PLA in the market for these applications, right? So it's going to be very expensive, or you're not going to go to these applications. Now you get a lot of recycled plastic that's from HDPE or polyethylene, but it's not 3D printable. What Cole did to this material, they made it a 3D printable material, so we reduced warpage, shrinkage, and also increased anti-oxidation of the material. So if you put, which is in the wood plastic composite deck, for example, you get from the store, they have antioxidants in it, and they are telling you 20 to 25 years, right? We've done a similar test in the lab, which is called the oxidation resistance, and we published that in peer-reviewed journals, that coal would act as a primary and secondary antioxidant. It would increase the life of the material. It would slow down. If you take an HDPE piece, throw it into the sun, it will crack before our material will crack because of fall. I hope that answered your question.
Yeah, that does.
But that's a very good question. Yep. All right. Any additional questions?
Thank you.
Thank you both.
Yep.
All right, our next stop is Ubaida and the rest of the team. They're going to talk about metal composites. Ubaida?
Hi, this is Ubaida, PhD student in mechanical engineering working under Dr. Al-Manjali. We're working on making ultra-conductive and cost-effective carbon metal composites. These materials find application in power transmission line, electronic devices, and magnet wires. Basically, we start with a pure carbon and aluminum foil, and then this material gets mixed with coal-derived graphite and graphene. And then these materials get hot extruded into either a wire or a strip, and you can take a strip with a wire across it. Once we have the final product, we test the electrical properties of this material. Here I'm showing the electrical conductivity setup that we use to test the electrical conductivity and temperature resistance. And then we look at the macrostructure of these new composites to see the effect of our process and this material, the macrostructure of these new composites. Advantages of this material include increased energy efficiency and current capacity, reduced cost, weight, and CO2 emissions. Thank you, and please feel free to ask any questions. Thank you.
There are no more questions? All right, we can move on. Right behind you, section.
Okay.
I'll be with you. All right. This is the whole group.
Alright, so my name is Edward Nyamiche, and I'm a graduate student with Dr. Tremblay, and I've been working on this process right here, which is aimed at recycling brine from oil and gas operations. So normally, brine from these operations have high levels of calcium and magnesium, which makes it hard to reuse. So our approach here aims at softening the brine so that we can reuse it. But fortunately, the reaction that we have over here does not really soften the brine, but it produces high value byproduct, which is calcium carbonate, and it has many industrial applications. So how we do this is by contacting the brine with CO2. That's why you see this bubbling brine, that's just CO2 going into the brine. So with the help of this process, we are able to make recycling more practical and cost effective. And then we are also able to produce high performance calcium carbonate. And when it comes to circular carbon economy, which is reducing the CO2 in the atmosphere, we have the potential to contribute because we are utilizing CO2 in this reaction. With recent work that I've been doing focuses on better understanding how this works and also looking into the properties of the calcium carbonate that we produce. So feel free to ask any questions. Thank you.
Thank you.
I'm Andy Kasich. I'm also a graduate student in Dr. Tremblay's group. My dissertation topic was on upscaling or upgrading ethane to ethylene by an oxidative process. That is valuable to the natural gas industry because ethane can then be sold as more valuable feedstock. The approach that was used in my project was to use a solid oxide fuel cell. This is an example of what one of the cells would look like. The darker portion there is the anode that has the electrocatalyst I would use. The ethane feed would flow across that cell, and then produce ethylene would be measured by the gas chromatography for the performance of the reaction. This, all told, is aimed at developing a more modular system that can be more versatily implemented in the oil and gas industry for this reaction.
Do you have any questions?
Sorry.
You're good. No, you.
Thank you so much.
Yeah. Oh, well, I think we have maybe another 20 minutes.
Yeah.
Okay. Sounds good.
Do you need to leave at any point?
So we're going to go up here.
Oh, I figured
Well, you would have to stop
I
that.
haven't met you yet. I'm a faculty in environmental program.
Oh, very nice to meet you. Yeah, I'm with the mechanical engineering department. I'm also associated with the
Yeah. long time?
10 years.
Oh, okay.
Yep.
Yeah.
Hi. So I'm Jay. So I'm a graduate student in Maji Research School. So our group focuses on electrochemical systems to help solve challenges in the energy, environment, and manufacturing sectors. So we focus on storing renewable energy from the sun or solar power, and then store it in flow batteries, or the alternative to lithium ion batteries, which you can store in large scale and use it when you don't have the sun or wind out there. And we also can use the same architecture to produce the chemicals in a much electrified way rather than using oil and gas or non-renewable resources. And also you can do water desalination with this architecture. So the architecture which we are focused on designing is we have a reactor, and instead of a solid electrodes we push through paste of electrodes, like carbon paste. So you can see we push this paste into the system so that the reaction happens all over the paste, and then you can scale up this process very quickly, and the process happens in a much more cheaper way.
So once it's
this
charged,
process
you can store it.
helps in scaling up the process. So we use different kind of instruments called shear mixer and rheology to see how easy it can push through, or how hard it's like if water or honey, so that we can use it in the reactor, and then we use potentiostat to impose current, and then find how much current or energy we are getting out of it.
So you know electrical engineering, or?
Yeah.
Alright.
Thank you.
How are you guys? I'm Brian Wisner. I'm an assistant professor in mechanical engineering. We focus on understanding how materials behave, how they respond to loads, talking mechanical, electrical, thermal, whatever you want. We mostly do mechanical and thermal loading, but chemical loading works too. And we also look at how we manufacture materials in order to improve those responses. And when I say materials, our lab focuses mostly on metals, but we do some work with polymers and composites as well. Just metals is our primary bread and butter. So on the screens, you can see some examples of some of the testing we do. So we use two primary methods to understand how a material behaves. One is vision, the other is sound. Materials make noise when they fail. You can also see how they fail. We augment that so we can see things at the micro scale. We augment that with like what you're seeing on this screen here, which is thermal imaging. So when we're doing high temperature stuff, that's actually the heat. So you're seeing the color as the temperature instead of typically what we see with our eyes. And we can observe how a material responds to that. And then we can either make recommendations on how to change the material to improve it, or use that to understand, okay, this is how the material responds, this is where we should use it as an application, and potentially this is where we should monitor it so we know it's failing when it's failing, and we can replace the components. So we have structural examples, but we also do this with things like batteries, where we can actually listen to the battery and it sounds different when it's in a pristine condition than if it's been damaged, at least when it's been damaged by cycling under really cold temperatures. We can also control just by changing the way we distribute the material. You guys are welcome to play with these a little bit. We have structure here, yeah. And then it's the same infill, but that's 25% solid material and 75% air. This is only 10% of the material, and you can feel the difference in how that behaves. Pass that around. I like that. That's a polymer example, but we can do the same thing for metals. So this is a solid, typically, structure, and then we can actually make a lattice structure. This one was designed as a bio implant lattice structure, so tissue can grow around it, or bone can grow around it. Or we can do this in a cost-effective manner. So this was actually produced on an Ender 3 $200 printer that you can buy off Amazon. Literally, I think we did buy some of those off Amazon. And this looks like a polymer, but then when you stick it in basically a really high temperature oven, it turns into solid metal. And then if you polish it down and test it, it's pure copper inside there. Copper with a little bit of oxygen. And that's because we did that in ambient. But the price difference is, that's affordable. That's something we can do quickly, customized, and somebody can afford. Whereas some of the other systems, they cost more, but we can fine tune it and change the microstructure at this scale. So these little white dots, they're at the micron scale, single microns, talking 0.001 millimeters, and we can control that, which determines how the material behaves. So that's kind of what we do. We also simulate some stuff too, but I live in the experimental world. Mostly the simulations are to inform us how to make things better.
Thank you.
Yeah.
Any questions?
So is the equipment used to build that here?
So that we used to build this one's not right here right now. That's over in stock, but we're still working on where here it's going to be. But so I work for a Center of Advanced Materials Processing. Half of our equipment is here, and on the other side of the green wall, you'll see the impact testing stuff over there. The other half's still over in the Stocker Center for the time being.
So you're planning to build
Yes.
it?
The hope is to have everything over here at some point in the not too distant future.
Great.
Yep.
Thank
Thank
you.
you.
Yep. All right, our next stop is CO2 mineralization.
Hello guys, how are you? So Yanni works in this, by the way, Yanni works in this project, so he has been working like for 6 months in this project. So welcome to the Electrochemical Enabled CO2 Mineralization Project. This project is sponsored by the Department of Energy, and the PI of this project is Dr. Jason Chen. So everybody knows, right, the greenhouse gas emission impact. So everybody has been experiencing global warming, sea level rise, and also ocean acidification in the pre-industrial era, right? So we are called to take actions to achieve this goal by 2050, right? One of the approaches is carbon capture and utilization, but it's basically the process that you are seeing here at pilot scale, but also at bench scale. This is the beauty of this project, right? As a chemical engineer, for me, it's very interesting working in both, scale. Another big issue that we have nationally, right, is the produced water or wastewater from oil and gas industry. Just to give you an idea about the problem, annually here in the U.S. are generating 21 billion barrels of produced water. And it's a very complex fluid with salts, contaminants. Here in Ohio, for example, in 2021, the state generated 32 million barrels. So basically, right, so we are impacting a lot of communities with the extraction of gas and oil. So the idea is to basically simultaneously valorize both ways, the produced water and also the CO2, using this approach, right? We are simulating flue gas in the industry because it's very hard to get the real, flue gas from a company. So we are mixing CO2 with air and then injecting through this sparger, like 5 liters per minute of flue gas in the reactor. The idea is to capture 10 kilograms of CO2 per day, and we are achieving that goal. Here you can see all the calcium carbonate that we are getting to these reactions, and the idea is to build, to create building material like this one. It's called cultured marble. It's basically a kitchen countertop having 80% of this powder that we are producing with wastewater. So, yeah, I don't know if you have any question or.
So, are you in your simulated flue gas? Like, what's the typical composition? What's the concentration?
Yeah, right now we are running at 25% of CO2, which is the flue gas from the cement or concrete, industry. But there are flue gases with less amount of CO2, like 4% or 12%. So the idea is also play with that variable, the CO2 concentration, to see how that concentration impact the morphology. Because something interesting here is that we are playing with the reaction conditions to get different polymorph of calcium carbonate. Right now, most of the calcium carbonate, the precipitated one in the market, is calcite. But there are a lot of interest in aragonite and barytite because as you can see, the morphology is different. So the surface area can be different. So we can create new building material with unique microstructures. So yeah.
So there were other contaminants mixed in with like that? Still, these will still be printed?
Yeah, definitely. Yeah, we that is the reason why we need to be very like picky selecting the application, because we have a strontium and barium. Yeah, but that is beneficial in our process because strontium and barium is helping us to get baterite and aragonite easily, because we are stabilizing. Baterite aragonite, you can just find them deep in the bottom of the ocean because you have high pressure. But here we are basically at environmental conditions. We are getting aragonite and baterite thanks to those contaminants. Right. Yeah. So we need to be selective. There are many applications for baterite and aragonite for biomedical applications, but in our case, because we have barium and strontium, I don't think so that we can use this calcium carbonate for biomedical applications. Yeah, more than 1 minute, but sorry.
No worries. So we have a hard stop at 3:30, right? It's 3:26. 26. We can go here and show you the last 3D printer. Okay, Jenny.
Thank you.
Thank you very much. Yeah, no problem. You can skip the attack tester. Okay. And I think we showed some interest in the additive manufacturing. Sean, sorry, we're skipping you.
No, that's fine.
They have a hot stop at 3:30. You know him?
Oh. I don't think so. Maybe. I don't know very well.
All right, so if you don't mind, Gianni, show them the 3D printer, and then yeah, very nice meeting you.
Yeah,
Thank
good
you
to
so
meet
much
you
for
too.
coming. Yeah.
Is this a movie?
Yep, and you guys put 3D printing? Yes. Okay, here's us like a tight schedule, so we're trying to skip straight to you.
Yeah, very nice meeting you.
Yeah, good
Thank
to
you
meet
so
you
much.
too.
Yeah.
Thanks so much.
This is the next section of the building. Do you know what they call this part of the building? And you see there's a lot of open space like this.
Oh, yeah.
They're still moving a lot over. I know they said like they're moving a lot from Stocker Center. I think all of the different organizations are moving. So I think they have a goal to have this building. I know. I remember thinking the goal
Zach, sorry. I'm Zach.
Hi, Zach, I'm Greg.
Greg, nice to meet you. Alright.
My name is Nisha Saila, and I'm Dr. Anajali's postdoctoral researcher. This is our largest scale or FGF 3D printer. The machine has a build volume of 36 by 48 by 48 inches. It has a single screw extruder and it uses pellet as feedstock material. So we use this machine to 3D print polymer and polymer composites. Composite can be just polymer reinforced with carbon fiber, glass fiber, or particles such as coal. So as you see, we 3D print different types of samples, negative and positive overhang, as well as the bridge sample to evaluate the printability of different types of materials. The main goal of using this machine is actually optimizing the processing parameters to make the final 3D printed composite good candidate for applications such as tooling and active housing. Yeah, if you have any question, I would love to answer your question.
So is this the only format you can print with?
No.
Yes, it should be pellet. Yes.
Pellet.
It should be pellet, yeah.
But like some are bigger, like some of these bags will be slightly. Is that Sabic or is that the carbon fiber?
That's the same.
Oh.
So yeah, it should be pellet.
So they're
it's not
slightly like different, right?
Okay.
But yeah, it's like this.
So if you had different composites, you can grind them up into this size, or
Yeah, the thing is, actually, we
print them?
mix the polymer with, for example, coal, and then we pass it to a twin extruder. We have the strand coming off, and then we pelletize the material to use it as feedstock for this.
So it has to go through.
Yes. Yeah. But it should be in form.
Okay. Great.
Thank you.
Thank you, guys.
Thank you.
All right. You can head over this way.
Is this something you printed?
Yes.
Yeah. Is that exactly this?
That one
Yes.
is the same. Yeah. This one took like almost 9 hours. That one is at 14 hours print.
Does this one have the full composite?
No, this one is glass fiber with ABS. Yeah. This one is the 60% whole with polypropylene. It's just material extruded out of the nozzle. To just have some idea what's the shape of the material. Yeah, made of coal and polypropylene.
Thanks.
Thank you very much for your time, of course.
All right. I know you had a stop at 3. There is more for the tour if you want to keep going.
Okay.
There's a second floor to the facility. So.
Yes, I did want to know what was on the second floor.
Okay.
Sarah, you don't want to come and see our lab?
You have time?
I have 4 minutes. I want to see it. I want to see it. Come on, let's see it.
We'll do a private tour for you later. Go.
Are you sure?
Yes.
Thank you.
So go. I'm just giving you a hard time.
Nothing personal. There's nothing personal.
You can head to the second floor. All right. I don't know if you remember, but last semester, me and another
Yes,
student.
you are very familiar. Thank you for reminding me where it was.
I was waiting for the right time to say it. Me and another student who also worked here, we were the two that were on the project.
Yeah. So how did that work out?
I think it
We
went
only
well.
met a couple times. I don't think I saw the final thing. Did I?
Yeah, I don't think so. It was more a project in another class. So we were learning about anaerobic digestion and how it can apply to pretty much anywhere of our choosing. And we were looking at Ohio University in general and what would we like to have more. Yes, and we're trying to see. We also talked to a company that does larger scale anaerobic digestion to basically find out why that's not the best idea for OU. And then we learned about smaller solutions too. So we were just basically showing them what the difference is here. I think it was
Still working on the small scale one.
I was about to ask you.
Yeah.
And do you work with
I actually was a manufacturer.
did you work with Mr. Sagan?
Yes.
Okay, I found that out after his son is my roommate.
Oh, okay.
So I was telling him about the project, and he's like, I think my dad's working.
Oh, yeah. Okay, so we can run upstairs real quick?
Yes.
Because I'll have to go in
Looks like we had something going on just inside the door.
Okay.
You guys.
Yeah. Not for the entire show, but you can go.
I just want to peek and see it.
And then if you want, you can leave the glasses down here. You don't need them upstairs.
Okay, so what if you say we need people down here who can kind
And there's still nothing on the third and fourth floor.
Right, they're moving things in, so there's equipment and supplies. I think maybe they're doing testing there, but it's nothing officially there.
Okay.
All right.
Going down.
So you have some stations kind of all around.
Okay. Are these labs too? Or?
Yes, this is more for microprocessing. It's different. Downstairs is Institute for Sustainable Energy and Environment, and this is different lab space. I think these, it says like different ones they have. Downstairs is also Center for Advanced Materials and Processing, but this is more for Yeah, semiconductor research.
Okay, well I'll have to come back another time because I don't really.
Yeah.
Are there stairs?
Yes, there are. Especially if taking physics talks. Let's see what it is. Here we go. Yeah, I think these went a lot longer than expected. A lot of people have a lot more to say. I do work with the carbon mineralization, and then David, who's the student lead, does work with the coalition